Cooley is from the Ocean Conservancy, and she joined there as the Science Outreach Manager in the Ocean Acidification Program just in January. Before that, she was a research scientist at Woods Hole Oceanographic Institution in Woods Hole. So thanks for doing this in your transition. I know it's a busy time. Today she's presenting an integrated assessment model for the U.S. commercial sea scallop fishery. So welcome, Sarah.
Thanks, Cassie, and thanks, Rue, and thanks everybody at NECAN for inviting me to do this seminar. Yeah, it's been a busy time, but we have a very exciting project going, so I'm happy to report out on it. I also really want to point out the involvement of my colleagues, most particularly Jenny Ruban, who's been working on this project at WHOI with us, and she's been a really critical part of it. My other colleagues at WHOI include Scott Doney and Dave Glover in the computational biogeochemistry group, and then our colleagues at NOAA who've been working on this with us are Deborah Hart and John Hare, who are at NOAA Northeast Fisheries Science Center. And then Tori Wu was a summer student we had who's at Boston College. This work was actually funded by NOAA's Ocean Acidification Program and then with the NCOS partnership. And I guess that introduces it. So today I'll be talking a little bit about the biology of sea scallops to start with. Placopecten magellanicus is the species we're talking about. Here's a little cutesy picture of it swimming, because I just think that's pretty funny that they swim and they behave that way. As a biogeochemist, I think that's quirky and cute. I'll talk a little bit more about environmental change and sea scallops and what we know, and then I'll talk a little bit more about the integrated assessment model, what our motivation was and how it's built. Then I'll show you some early results from the model and tell you about our future plans for what we're going to do with the project. So here's the sea scallop. On the right is sort of, the sea scallop in the wild, and on the left is a picture of the sea scallop's innards. And what we really harvest them for is this adductor muscle. Some of the fishery also harvests the roe, but primarily the fishery is built around harvesting this adductor muscle. The scallops are shucked at sea, and then the shell and the other innards are put back overboard, so what harvests are, the weight of harvests that are measured is actually the weight of the mussel itself. So sea scallops have a life history that takes them through all parts of the water column. They're broadcast spawners, and they spawn once or twice a year. It takes 2 years until they reach sexual maturity, which is about 40 millimeters in width or length. And then it takes another 4 to 5 years total until they get to a harvestable size, which is about 90 to 100 millimeters. On the right here is a sort of a life history cycle. Once the scallops reach this point at the top of the wheel, they settle into the benthos, and so then they live near the ocean floor, and they can swim to get away from things like you saw in the previous slide. But when they're new juveniles, early juveniles, and adults, they live in the benthos, and then the other stages on the other half of this life history cycle, the eggs, the early larvae, and then the footed larvae, those are all occurring in the water column. I also wanted to point out that these grow at the outer borders of their shells by laying down calcium carbonate, and that's actually a feature conserved across all mollusks, and that is a process that has been observed to slow in ocean acidification conditions. So the scallop habitat is very abundant along the northeastern Atlantic shelf at about 40 to 100 meters. The fisheries are located in the mid-Atlantic bight along the Delmarva Peninsula, New Jersey and New York, Georges Bank in that whole area, and in the Gulf of Maine. And they tolerate water temperatures of about 0 to 18 degrees Celsius, but they are most commonly found in water temperatures about 5 to 10 degrees Celsius. The largest scallops are found in Georges Bank, but there's a higher abundance found in the mid-Atlantic, but they tend to be smaller in size. So there's some different growth characteristics that you find in the mid-Atlantic bight populations and the Georges Bank populations. The Gulf of Maine population is somewhat smaller, and only recently has the Gulf of Maine area begun to be managed along with the Mid-Atlantic and Georges Bank populations. So the fishery itself is one of the most valuable single species wild-caught fisheries in the United States. It's currently worth about $500 million a year in ex-vessel revenues. Now the red bars actually indicate the landings, and then the black dots indicate the value. And the value is the nominal value, so it's not inflation adjusted over time. The fishery was considered overfished in the mid-1990s, which led to a number of new management strategies. Managements were placed in terms of access, like who could actually get permits to the fishery, where the fishing locations occurred, how the effort was allocated by different types of vessel. The actual gear size of the dredge rings was regulated, and the crew size was limited to 7. And so what we saw as a result of these different management policies that were put into place was some real changes. So in around 1994, the limited access fishery rules were put into place and certain areas were closed. And then in around 2000, rotational management of these different sub-areas was put in place. And then even later, the gear was restricted from 3.5 inches to 4 inches. And with each change, there was seen a big jump in the population. So the management efforts have been considered to be a success, and the fishery is viewed to be doing quite well. So sea scallop landings in general are divided into a couple of different categories. So on the left is the plot that we showed a moment ago, and then this gray box on the left is kind of blown up on the right. And so this right-hand plot shows the landings as divided into size classes. Now scallops, as I mentioned before, are classified according to the number of scallop mussels per pound. So the dark red is under 10 meats per pound. The darker red is 10 to 20 meats per pound, and so on. So what we find is that the management favors the growth of larger scallops because there is a price premium for the U10 scallops. The price premium can be as small as 50 cents a pound, or it can be as much as $2 to $3 a pound. So there's a real incentive to let those scallops grow and reach a larger size. There has been some hint that sea scallop is experiencing climate change impacts. There may be a shifting of the scallop range to higher latitudes associated with ocean warming. But management doesn't currently incorporate long-term climate change. The reason that we think that there may be potential shifting is that in 2013, there were only about 4 scallops in the entire Virginia Beach closed area right here on the red circle. And they're beginning to find calico scallops in this closed area too. Calico scallops are a smaller subtropical species, and they're moving northward. Another thing that may be climate linked is we're seeing a lot of predation from sea stars in the more southerly locations for the scallops, and there's some indication that that may be a temperature-linked phenomenon. But we're not going to be looking at that in this particular iteration of the model. That's sort of something that we might look at in the future, but we're not doing right now. We're just looking at environmental factors only in terms of direct impacts. So when we think about what we know about ocean acidification and mollusks, there's a large body of literature showing that mollusks experience significant negative impacts from ocean acidification. And here I've excerpted 2 plots from Christy Croker's meta-analysis. On the right is a plot focusing simply on mollusk results. What we see is the mollusk larvae have lower survival, lower calcification, lower growth, and lower metabolism. Juveniles are kind of a mixed bag, and then adults have significant decreases in calcification only. And so all told, scallops mollusks are the taxon that are doing the worst in terms of ocean acidification when we look at it holistically. The survival is, on balance, the lowest. Calcification is impacted the most, and growth and development are also impacted pretty significantly. So ocean acidification's effect on sea scallops has not yet been studied yet. So we really need to infer the possible effects of acidification on life history stages. Now this dashed line reminds you of the benthic and pelagic forms of the species. So during this side of the life history cycle, the scallops are living on the seafloor. Now during this side, the farther, I don't know, the downward side, it's not the south side, but anyway, it's the lower side of the cycle, they're living in the water column, in the upper water column, where they're living planktonically, and they're subject to a lot of predation by omnivores in the water column. Now we've put a star next to the stages where we have the most evidence to suggest that there could be ocean acidification effects. Ocean acidification's effects tend to affect the youngest larvae. There have been a lot of studies showing that mollusk larvae, just a few days old, are most heavily affected by ocean acidification. They're not able to put down their shells as skilled, or the shells are malformed, and the shells are growing more slowly at that time. And then there also might be reason to suspect that broadcast spawners are going to be affected. There are other broadcast spawning species that exhibit decreased spawning as a result of acidification. So we think that these could be sort of the bottlenecks in terms of ocean acidification response on sea scallops. So changing gears a little bit, just to look at the carbonate system in New England. These are two selected plots from Nathan Rebuck's work that's in preparation. He gave a NECAN talk a few weeks ago, which was really very good. If you're interested in this topic a little bit further, I'd suggest that you go back and have a look at his talk if you haven't seen it already. What we see here is the seasonal cycle. The area experiences seasonal cycles in pH and saturation state, as well as other carbonate system parameters. So in the Mid-Atlantic Bight, which is the small dashed line, which is where a lot of the sea scallop population lives, we see a pH high of 8.1 and a saturation state low at that time of about 1.9, and then the pH decreases all the way down to about 7.99, and saturation state is about 2.8. So we see a pretty large seasonal cycle for the Mid-Atlantic Bight. And the Gulf of Maine, as you can see, is a much smaller seasonal cycle. But we do see variability in surface conditions in this area. When it comes to deep conditions, we have less data. But the GOMEC 1 and 2 cruises are in the process of showing what is going on there. And unfortunately, this plot is sort of cropped oddly now that I've changed systems. But actually, it's completely the wrong part of the plot. I'm sorry about that. What we saw from Alec Long's paper presenting the GOMEC 1 data, and also the GOMEC 2 data presented by Rick Wanenkoff in December, is that in the Massachusetts and New Hampshire areas, saturation states at about 50 to 100 meters, where the scallop larvae, or the scallops, the settled scallops, are living. It's probably between 1.5 and 2 in saturation state, and that really meshes well with Nathan Rebuck's work, and it also helped us actually put boundaries on our biogeochemistry model. But the scallops are living in areas that are oversaturated, and not by a lot, but the seasonal cycle isn't taking them very close to the undersaturation threshold. So we wanted to put together an integrated assessment model that would go ahead and consider the sum total of biogeochemistry, population dynamic responses, and socioeconomic factors for this resource. Now, sea scallop was an especially good candidate for this kind of model because it's very, very valuable. Its population dynamics are really well established, And the oceanographic environment is relatively constant with set seasonal cycles compared to, for example, bay scallops, which live very close to shore and have much more influences on the biogeochemistry that they're seeing. So for the scallop model, we put together a von Bertalanffy growth matrix-based model, which was adapted from SAMS and CASA, which are the two major spatially explicit models used to manage the fishery by NOAA nymphs. In the biogeochemistry side, we created a two-box biogeochemical model that's driven by seasonal thermal stratification. And then in the economic side, we put economic decision-making and relationships from that were based on statistical relationships gathered by NOAA NIMS Economics branch. And here's the integrated assessment model in full detail. And I know your eyes are probably boggled right now, but what I wanted to point out was that in the biogeochemistry model, which is in the orange colors, the surface ocean and the deep ocean are depicted separately. And so the larvae are living in this surface ocean conditions. And then when they settle, they experience the deep ocean conditions. And in the scallop model, we've set it up so that we have the pre-recruits, which are kind of implicit. They're not explicitly modeled in our equations, but when they enter at 2 years, they've experienced the sum total of all of these other factors that may be affecting them in the pre-recruit stage, for example, changes in spawning or changes in growth. And then when they're recruits, then they can grow to the fully recruited stage, and in both cases, then they can be harvested. And in the socioeconomic model, it runs a little bit differently because it has a few decision points in it as to whether that feed into the decision of whether to fish one more day. And that involves a profit analysis, a market analysis, a rules analysis to make sure that we haven't exceeded days at sea or crew or anything like that. And then we can harvest if we can fish one more day. So one of the biggest challenges to this is to figure out how we can examine ocean acidification's effects on sea scallops. And like I said before, the response hasn't been determined. And so what we've done is we've gone ahead and we've put in code into the model that allows us to explore the effects of changes from ocean acidification on the spawning, on the early larvae, and on the newly settled larvae. And so what we've done is we did a meta-analysis of the literature to determine quantitatively how pH or omega change was going to change scallop growth. And these plots show our results. On the left is the relative change in pH. On the right is the relative change in saturation state. And these are relative units, by the way, there. So that's why you're seeing 25 or 50 or 75 compared to, the units we think of for saturation state, which is like 1, 2, or 3. So what we did was where the controls reported in each experiment were the 0 point, and then the results for the experiment were everything sort of beyond that. And we found that we had a very good relationship between decrease in pH and saturation state and decrease in growth of adult mollusks. And mind you, we did this for adults only. We did not go ahead and get into the larval studies because that was very challenging, and we didn't have the kind of species breadth that we needed to do this. But the question remained of how do we actually put that into a von Bertalanffy growth equation. So we're using site-specific von Bertalanffy growth relationship. Whoops, and the equation has dropped out. Sorry about that. What this von Bertalanffy growth curve does for us is it parameterizes growth as this kind of a curve where we have very quick growth in the early ages, and then as the scallop gets older, the shell height or the shell width kind of reaches a maximum. And our hypothesis was that ocean acidification reduces the rate of growth, but it's unknown whether ocean acidification affects the maximum size. None of the studies that have been done have really shed any light on that yet. And so what we decided to do was only to tinker with the parameter that changes the early growth characteristics, and then we decided that we would allow them to reach that total size anyway. And then, so that's what we did. We reduced the growth rate, which is K in the von Bertalanffy growth equation, which I would show you if it hadn't dropped out. And we also put in a temperature relationship from Heilmeyer et al. In 2004. They did a study for pectinid species that showed that with increasing temperature, you get increasing growth. And so when you take ocean acidification alone, you only get a decrease. But when you put ocean acidification and warming together, which is what we see in a future ocean, we actually get sort of the middle scenario. And what we did to be most conservative in this case is basically just to make those conditions additive rather than synergistic or anything like that. So for recruitment, we assume a Beaverton-Holt stock recruit relationship. And we assume that the ocean acidifications is very likely related to larval survival. But this is complicated a little bit by nonlinear dynamics. You can't simply just cut larval survival by 50%, assuming that your stock recruit has changed a little bit. So what we have here is if you have a spawning stock biomass of about 100,000, the annual recruit is probably about 1,500 million individuals. So if ocean acidification reduces the spawning stock biomass by 50%, this actually doesn't give you a 50% decrease in the recruits. Oops, it winds up giving you a 17% reduction in recruitment. But if you have a low spawning stock biomass, a 50% reduction in that gives you a much larger reduction in the spawning stock biomass. But if the system is saturated with larvae, like it is in George's Bank, reductions in larval survival, moving sort of this way towards the origin, you have very little influence on recruitment. So we went ahead and we included that type of relationship in the model so that we could be most accurate or do the best we could at sort of taking a stab at that. And here is an example of our early population model results. We have a very good match between the observed population structure from the annual studies that NOAA does, which are, it's hard to see, but there's a dotted line around this part of the plot, and that's what we're blowing up here on the plots on the right. And so our observed structure matches our model population structure, which is the whole gray bubble plot. And then our population size, our size structure also matches pretty nicely. So the red is the observed, and then the blue is the modeled. And so we're seeing a pretty nice mirroring effect here in both cases. So we feel pretty good about that the population model is giving us results that are representative of the population. We do have stochasticity in the recruitment and in the model, so we don't get identical results, but what we're seeing is a size structure that evolves over time the same way that the observed population. And so we feel very happy about that. We've also modeled the harvest data. The black bars show the actual revenue on the top and the landings on the bottom. And then the open bars show the modeled results for that. And again, we see that the revenue follows the actual results quite nicely, the modeled revenue. And the modeled landings also follows the actual values nicely as well. When we turn to the biogeochemistry model, we see that we also get a very nice match between the biogeochemistry model output and the observations that do exist in the area. So what we have shown here is the solid line is the box model. The dashed line is the community ecosystem model from NCAR, which is a coupled ocean atmosphere model that is sort of three-dimensional and much more complicated. So it has, we wanted to just kind of see how it fits in this area, and we see some very nice agreement between those two models. And then the open bubbles are results from the SOCAT data set, which is the surface PCO2 anthology that's being sort of finalized now. And then the dark bubble is the values gotten from the GOMAC 1 and 2 cruises. And so what we feel very confident that the biogeochemical model is also doing a good job in the area. So when we go ahead and we run the integrated assessment model to 2050, we've done it here in 3 ways. We have the red as the control, which is sort of just year 2000 conditions extended into the future just to make sure the model is stable. We have ocean acidification only in the blue trace, and then ocean acidification plus temperature in the green trace. And what we see is that in the ocean acidification and OA plus temperature scenarios, we have a progressive decrease in deep pH and in deep saturation state. We have a progressive decrease in biomass that is fastest with ocean acidification only. We also have a decrease in revenue. And a lot of that decrease in revenue has to do with the decline in U10 scallops that is observed in the model. And that decline in U10 scallops is primarily because we're seeing them grow more slowly, so it takes them a lot longer to attain that, biggest size. And they tend to get fished out before they reach that size. So what's next for this is we will be doing a lot of sensitivity testing, and this is just sort of a little bit of a list of the things that we can test in terms of the model sensitivity to the different parameters within each model. So on the scallop side, we can test things around mortality. There are a couple of different kinds of mortality in the scallop model. There's incidental mortality, there's natural mortality, and discard mortality. Incidental is kind of just, breakage. Natural mortality is, they get old and die. And then discard mortality happens if they're fished, they're actually too small to keep, and then they die on the side. And the growth-related things that we can test are whether or not the rate or the maximum size makes the biggest difference. If we adjust the rate for ocean acidification or the maximum size attained, does that make a big difference? How does spawning affect the population and the outcome, and how do recruitment affect? And what we find is that for recruitment and spawning, and also for the early growth rate, those things kind of nest together because recruits don't enter the model until they're age 2. And so all of the larval stuff kind of gets sort of conflated together and gives us recruits at a certain time that are the sum total of what they've experienced. The next things we also have on our plate is to test the effects of the biogeochemical model. We have physics. We can test physics, in terms of the effects of wind or vertical diffusion. From the biology side, we can test primary production, the F ratio, the pick-to-cock ratio in the model, or the remineralization rate. Those are all sort of the things behind the scenes in the biogeochemistry part of the model. And we can also test in the socioeconomic model. We can test sort of more scenarios. We can test whether or not what happens if the import-export balance changes or stays the same. We can test effects of price changes because this is a very high-valued commodity. Price changes may or may not have an effect on the overall outcome. We can look at costs for labor and overhead. To see if external economic situations change in the future, what could be the outcome on that. And then we can also test the effect of different rules changes. We can test what happens if we do change the amount of days at sea permitted, the crew sizes perhaps, gear size, things like that. And then finally, one thing that we haven't actually put into the model, but we're kind of kicking around, is whether or not to start getting spatially explicit. Like I said before, we don't get as spatially explicit as the models used for current management of the fishery. But we've been kind of thinking about what might be the effect of that. Because when you think about the different areas from an environmental standpoint, acidification will be occurring at a different rate in each of those areas. Temperature increases will be also happening at a different rate. And so that could be a really interesting aspect of the model to look at. So we've started doing some of the sensitivity testing, and what we find is the model is very sensitive to changes in certain parameters of the scallop model. So discard mortality, it's not especially sensitive to that. So actually, I should also point out let's see, the red lines are the normal, the normal trace, in terms of like the everything the way we think it should be. The dashed lines are what happens when we half that parameter, and then the solid lines are when we double that parameter. And so the model is not very sensitive to discard mortality, but it is quite sensitive to whether or not we have the incidental mortality parameterized correctly and the natural mortality parameterized correctly. So that points to something that we really need to know. Is ocean acidification possibly going to change these type, the scallop sensitivity to different things, and is it going to change their mortality rates at, related to sort of breakage, or just do they get old and die faster? For the biogeochemistry model, we find these are actually on the same y-axis as previously, so they look kind of squished, but it gives you a sense that the model is really not as sensitive to changes in the biogeochemistry. The biogeochemical factor it's most sensitive to is changes in the remineralization rate. And then when we go ahead and zoom in a little bit, you can get a little bit better sense that we have remineralization rate is really the king, but then we have sensitivity to some of the wind and then the F ratio as well. So we're still kind of trying to interpret these results, but this is where we're heading next. Because looking through all of these factors, it's going to give us a sense of the major and minor levers that we have on the system to adjust the system, or that will be externally adjusting the system. So just to sum up rapidly, we find that the fishery is, because the fishery is doing well, it's a very good time to think proactively about global change and how do we anticipate global change affecting this resource into the future. And one of the challenges here is that global change is occurring on a much different time scale than year-to-year management. And so this model represents a tool that we can use to kind of bring those two things together and really try to get ahead of global change in some ways. We also know, but this tool really underscores the knowledge gaps we have about ocean acidification and this particular species, Placopecten magellanicus. The model sensitivity to details in especially the scallop biology underscores the fact that we really need to close those gaps, and we need to know exactly how ocean acidification and temperature will interact, but also how ocean acidification will affect population characteristics of this species. For example, are they going to be more likely to be crushed? Are adults going to be more likely to be crushed in the future? Or are we going to have higher natural mortality just going forward? And if so, what would be that value? Because knowing that information is really critical to making sure that this model is simulating what we have going into the future. And what we tested is, I also didn't actually say when I was going through the integrated assessment results, we are looking at a CO2 emission scenario of the sort of business as usual. And while this doesn't paint a very positive picture right now, we're hoping that as we go forward, we can identify these levers in the system, whether they be on the human side or in the population dynamic side, or even in the ocean chemistry side that exist, that are going to allow us to perhaps hit a balance. It would be great if we could find some kind of a balance that incorporates, that basically is a win-win for the fishery and for the resource itself. We don't know if that exists, but we're hopeful. And it's very certain, though, that this tool is going to be able to identify which factors are actually driving certain outcomes, whether it be a harvest factor or an environmental factor. And I think it's going to really fertilize the conversation among decision makers that's very practical and solution-oriented. And one of the things that we are heading for is we are going to be completing the sensitivity analysis. We're going to be testing adding these spatially explicit details, which is going to give us even more insight into what factors are affecting the fishery. And then we're going to build what we're calling a model dashboard. And this dashboard is going to provide non-modelers a way to experiment, well, maybe not experiment is the right word, but explore the model outputs for a number of different scenarios and go into planning discussions with a very clear sense of how much different activities might affect the integrated system. And I think that's going to provide a much more sort of practical way for different groups to discuss what factors are most important to them and what factors are most important to the fishery. So this is sort of, very much a work in progress. This has only been the first, not quite 18 months of the project, and so we still have a long way to go. But we're very excited about the promise that this model has, and we're going to be putting it through its paces here in the next few months and learning a lot more about the model itself and developing those scenarios that will inform the decision support dashboard. So with that, I'd like to thank you all very much for your attention. I know it's hard with a webinar. It's hard for me to read the crowd.